So we're looking at composition of functions, then we're going to look at inverse functions, exponential functions, and logarithms, kind of a review. So I'm going to try to go through this pretty fast. And this is chapter 6 in our textbook that we're looking at. The composition of functions. So notation-wise, there's a couple different ways that you can write it. So F little circle G, and then parentheses around that whole thing, and then a parentheses with X. What this is saying is, another way to write it, which to me makes more sense of what you're doing, is F parentheses G parentheses X. And we kind of read this as F of G of X. And what we're doing is we're basically taking our equation, g of x, and wherever we see it in x and f of x, we're replacing it with that. Okay, so for the domain of a composition of functions, well, when you're doing f of g of x, basically, if you're plugging in a value for x, the first thing that you're doing is you're plugging it into the g of x, this inner piece. And so once you plug in a value in for x for g of x, you have some output. Well, we have to worry about that output being in the domain. It has to be in the domain of f of x, because that output is then being put in to that value of x of f of x. And so the domain of f of g of x, we have to, it has to be, it's the domain of g of x plus any value of x, which makes g of x undefined for f of x. Just going to mute everybody. And if you have a question, let me know. Okay. Okay, so let's look first at the following. So let's say you had f of x is equal to negative 4x cubed plus 5x squared plus 8, and they phrased this weird. I'm in the wrong section. I'm in the chapter 5. Let me just change this. Sorry. Okay, let's start over. Let's say we have f of x is equal to 3x plus 2, and g of x, this is equal to 2x squared minus 1. So notation, first thing they want us to find is f little circle g, and then and your parentheses, and then parentheses 4. So I tend to like to write it the other way, and this we can write again as f, then parentheses g of 4. So work inner and then working outwards, and so g of 4. This is saying what it, plug in 4 for x. Or you see an x in g of x. So if we looked at g of 4, this would equal 2. You see an x, put parentheses squared minus 1. And so going back in and plugging in 4 wherever we see an x there, this gives us back order of operations, square the 4 first. 4 squared is 16 times the 2 out front is 32 minus 1, which is 31. So g of 4 is 31, and so this is going to give us f of g of 4 is the same thing as f of 31 and that's telling us to go in and wherever we see an x now in f of x, we're going to rewrite and plug in 31. And so we have 3, put parentheses where you see an x, and then plus 2, replace x with 31. So we get back, this is equal to 3 times 31 is 93 plus 2, which is 95. So there was a couple ways that we could do this. Because it already gave us that value for x to plug in, I just did it this way. But if they hadn't done that, they could have said, what is f of g of x? So let's say find f of g of x. So that would be telling me I'm going in wherever I see my x and f of x, I'm going to rewrite it with g of x. So if you wanted to, we could rewrite this as f of, well, g of x is the same thing as, 2x squared minus 1. And so now if we go in, wherever we see an x in f of x, we're going to replace it with 2x squared minus 1. And so let's just go in and put parentheses wherever we see an x in f of x. So 3, we see an x, parentheses, big enough to put that in parentheses, and then we see plus 2. Rewriting and putting 2x squared minus 1 wherever we saw parentheses. And so we can simplify this a little bit. We can distribute that 3 inside the parentheses. And so we have 3 times 2x squared is 6x squared, and 3 times negative 1 is negative 3. And then we have this plus 2 outside, combine like terms. We have 6x squared, well, negative 3 plus 2 is minus 1. So technically, from this point, we could do part A. If we had plugged in 4 into this equation, wherever we saw an x, we better get back the same thing we got up here. So f of g of 4 well, up here, this is 6. You see an x, put parentheses, we're going to square it minus 1. So plug in a 4 where you see the x. So we get 6 times 4 squared. 4 squared is 16 minus 1. So 6 times 16. Well, 6 times 6 is 36. Carry my little 3. 6 times 1 is 6 plus the 3 is 9. So that's 96 minus 1, which is 95. Okay, so they're the same thing. B might be better to go first if you had to evaluate f of g of x at multiple values, because then you already have that and you've done all your work. Where here, if you were just evaluating it at one number, that was fine. Let's say it asked you what the domain is. Of f of g of x. Well, if we look at the domain of f of x, I'm sorry, we have to look first at the domain of g of x, the inner piece. Well, if you go look back, it's a polynomial. It's 2x squared minus 1. Polynomials are continuous everywhere. They're defined everywhere. We don't have any problems. There's no trouble spots here. That's going to give us a value that's undefined. So our domain of g of x are all real numbers. The domain of f of x, well, it is also a polynomial. That was 3x plus 2. So it's also defined everywhere. So there's no spot that we have to exclude that we're getting back from g of x that will give us a problem in f of x. So since the domain is all real numbers for both, then the domain of the composition is also all real numbers. We need to be careful. Order of compositions normally matter. And so if you take the order and the composition in the other direction, usually you don't get back the same things. Sometimes you do, and you do in special cases, and we'll see that a little bit later with inverse functions. So let's say it asked find, oops, thinking ahead, find g of f of x. So this is now telling us to take our equation of f of x. So our equation of f of x, oops, what was that one? So f of x was 3x plus 2. And we're going to plug that wherever we see an x in g of x. So g of x, that was 2 times x squared minus 1. So it's 2, we see an x there, let's put parentheses, squared minus 1. So we're putting in 3x plus 2 wherever we saw a parentheses or put a parentheses. And now we need to simplify. So if we distributed out 3x plus 2 times 3x plus 2, well, 3x plus 2 times 3x plus 2, 3x times 3x is 9x squared. I'm going to have to add my two middle terms, and that's a 6x plus a 6x, so that's a plus 12x. 2 times 2, so plus 4. So that's that FOILed out. And then my minus 1. So let's distribute the 2 and then combine like terms. And so distributing the 2, we get 18x squared plus 24x plus 8. And then we have this minus 1 outside. So we only have two terms that are like, so 18x squared plus 24x, and then 8 minus 1 gives us plus 7. So notice this is not the same equation that we got of f of g of x. That one was the 6x squared minus 1. And this is 18x squared plus 24x plus 7. So order is going to matter when you're plugging in which equation into what. Let's say instead f of x is equal to x raised to the 3/2 power, and g of x is equal to 2 all over x plus 1. Let's find the domain of f of g of x. Okay, so a couple things we need to do. First, we need to look at the domain of our inner piece, which is g of x. So the domain of g of x well, looking at g of x, there's only one value that's going to give us a problem, and that's the value which sets our denominator equal to 0. And so our denominator equals 0 when x is equal to -1. So our domain of g of x, this is going to be all x such that x does not equal -1. Okay, so we can plug any number in and we'll be fine for g of x. Now let's look at f of x. So the domain of f of x. I'm just going to rewrite it again as 3/2. Well, maybe you'll see that this actually is going to have some problems. Let's look at x of 3/2 as a radical. So remember that if you have a rational exponent, that could be rewritten as a radical. And so this is the same thing as the square root of x cubed. The denominator is what index that you have of your radical, and the numerator is the power of that base. So I can't have x cubed minus 1 cannot be less than 0. If that's less than 0, then I'm not getting back a real number. And so x cubed has to be bigger than 0. In order for this to be a real number. So we could solve for this, right? We could take the cubed root of both sides. And so if we took the cubed root of both sides, well, the cubed root of x cubed greater than the cubed root of 0. So x is greater than 0. So the domain of f of x, all my values of x actually can equal 0. Because that's not in the domain. And that's not in the denominator. The problem is when we plug in values for x for g of x, we might get spit out something that is negative. And if we spit something out that's negative, that's then going into the function of f of x, and that's undefined. So because of g of x, or f of x having to be greater than or equal to 0, we have to look and we have to say, okay, well then g of x. So therefore, if you see this kind of 3 dots that form a triangle, that's kind of shorthand for therefore. You might see that later on in your class. So therefore, we have to say that g of x has to be greater than or equal to 0. Okay, so we have to solve for that. Well, g of x, that was 2 over x plus 1. So we need to look at when is 2 over x plus 1 greater than or equal to 0. Okay, so kind of a good review. We looked at rational inequalities. So when we're looking at these rational inequalities, we can think of graphs or we can think of it algebraically with test points. So there's no x-intercepts, there's no value which sets our denominator equal 0. The value, this is undefined, which we already discussed, was at -1. This graph, if we graphed it, we know there's a vertical asymptote at -1. So it could change of being above or below the x-axis there. And so we need to test points on each side of -1. So if we chose a value to the left of -1 and we plugged it in here, we want to see if it's positive or negative. And so if we chose x equals, let's say -2, not smaller than -1, if we plug it in here, we get 2 over -2 plus 1. So we get 2 over a -1, which is less than 0. So this is false. Any number you chose to the left of -1 would give us a negative number, and that would be undefined. And so now look at a number that is bigger than -1. So let's look at x equals 0. So if we plug back 0 into this equation, we get 2 over 0 plus 1, which is just 2 over 1, which is greater than 0. And this is a true statement. I guess we can say that. And so our domain or our values of x, which would give us positive numbers as outputs for g of x, has to be bigger than or equal to -1. The problem is it cannot be -1 for g of x because it's undefined there. And so our domain for the composition of the function has to be the union of those two sets. Or not union, the intersection, what they have in common. So sorry. So x had to be here greater than or equal to -1. But x cannot be -1. And so our domain is x such that x is strictly greater than -1. So let's say you're given two functions, f of x, which is x over x plus 3, and you're given g of x, and this is 2 over x. So let's first look at f of g of x. So this is saying, let's look at f of 2 over x. So wherever we see an x and f of x, we're going to replace it with 2 over x. So let's go in and put parentheses wherever we see an x in our f of x. So we see a x parentheses all over, you see an x parentheses, and then a plus 3. So rewriting that with 2 over x. And then we want to simplify this. We have a complex fraction. We have fractions within fractions. And so we don't like fractions within fractions, and we can get rid of those fractions within fractions by either getting the numerator as a single fraction and the denominator as a single fraction, and rewriting it as a division problem of fractions, which is multiplying the numerator by the reciprocal of the denominator. I think that's harder. The other way is to look at your common denominator of all the fractions within, which is just x, and multiply by a fancy one by your LCD so that that goes away when you distribute. So you can think of it as x over 1 if that helps you. So when we distribute x over 1 to 2 over x, you're just left with the 2 all over. And so we have to distribute this to each piece in the denominator. So 2 over x times x, x's cancel, you're just left with a 2, plus, well, there's no x or anything in the denominator here, so it's just 3 times x, 3x. So this is f of g of x. What if it said find g of f of x? So this time you're plugging in your equation f of x into g. And f of x is x all over x plus 3. So we're going to go into our equation g of x, and wherever we see an x, let's put a parentheses there. So we have 2 all over, there's an x there, so let's put parentheses. And now we're going to put in that parentheses what we're evaluating at x all over x plus 3. So you can think of this as 2 divided by a fraction, x over x plus 3. So this is 2 times the reciprocal, x plus 3 over x. If we distribute our 2, we get 2x plus 6 all over x. Okay, so you've pretty much been doing sometimes composition already in our class when we were looking at the difference quotient f of x plus h. So you could have thought of a function being x plus h, and you're plugging that in wherever you saw an x in your f of x function. It's helpful when you get into calculus to be able to go the opposite direction. So given a function, being able to break it down as a composition of 2 functions. And there's an infinite different number of ways that you can do that. Some are easier than others and more recognizable than others. So let's say you have the following. So you're given h of x, and it's defined, let's say, to be 1 plus 3x quantity squared. And it says find f of x and g of x such that h of x equals the composition of the 2, f of g of x. So I kind of go and I pick out what is my inner piece. Your inner piece, typically, if you have parentheses or something repeating itself in your function, choose that to be the inner piece. So in this case, I have parentheses, I only have one thing, one grouping. So I'm going to choose my inner piece to be what's inside that parentheses. And so if we choose g of x to be this 1 plus 3x, so basically we can now figure out what f of x is. Well, f of x has to be where if we see this 1 plus 3x, we need an x there. And so I see this 1 plus 3x, I need an x there, and then it has to have everything else in there. So my f of x value is going to be x quantity squared. So check it out. If you plug in g of x, wherever you see an x in f of x, we get back h of x. And so these would be the two functions that could do that. So what about h of x is equal to 1 over the square root of 5x minus 1. So same directions, find f of x and g of x such that h of x is equal to f of g of x. So let's do it two different ways. What if we just choose it to be what's underneath the radical? And so if we chose g of x in this case just to be 5x minus 1, then f of x would have to be one over square root, well, instead of having 5x minus 1, that's our g of x value, we need just an x there. So that's one possibility. But what if we had chosen g of x instead to be the square root? That whole denominator, the square root of 5x minus 1. So basically for f of x, wherever we see with square root of 5x minus 1, we're just going to rewrite it with just an x. So this would be f of x is 1 over and then just an x. So it really depends on what you let your inner function be, determines what the outer function is going to be. Okay, so inverse functions. So a couple things have to occur in order for a function to have an inverse. So inverse functions have the following property. Notation-wise, if we're looking at the inverse of f of x, then f inverse is written with, and it doesn't mean the negative exponent, but it's written with f with a little, looks like a -1 exponent of x. Okay, I just needed to have that notation now. So inverse functions have the following properties. Basically, if you take the composition of the inverse, a function and its inverse, you'll get back x. It doesn't matter what direction. So if you took the composition of f inverse and f of x, you'll also get back x. So that has to hold true. And if you show one way, then as long as your math was okay, then the other way should work. And I'm okay with you just showing one way. So other instructors might want you to show both ways. The domain of f of x equals the range of f inverse of x. And the range of f of x equals the domain of f inverse of x. So if you recall, when you were trying to find inverse functions, if a function had an inverse, basically you rewrote your equation, you swapped your x and y values, and you solved for y. Swapping x and y, x is your domain, you're swapping it for your range for your inverse function. The range is now going to be, y values are now becoming x, so your range is now becoming the domain. So if x, y, so another way to say this too, and this will help if you're looking at graphs, if x, y is on f of x, then y, x is a point on f inverse of x. One other property, graphically, f of x and f inverse of x are symmetrical across the line y equals x. So let me just do it as a dotted line, right? If we graphed y equals x, that's just that vertical line, not vertical, diagonal line, going through the origin and strictly increasing. Every x value is the same as your y value. So basically it'd have to be a mirror image across this line. In order to have an inverse, it has to be a one-to-one function. So a function that is one-to-one has an inverse function. Okay, so one-to-one functions are special functions. So recall, to be a function for every value of x, you get back one value of y. And so it was okay for different values of x to give us the same y and still be a function, but one value of x couldn't give us multiple outputs. To be one-to-one function, every output also has to be unique. So there can't be the same value of x that gives you this, there can't be different values of x to give you the same y value. And so functions, we looked at passing a vertical line test when we looked at graphs. One-to-one functions have to pass both the vertical and the horizontal line test. So one-to-one functions. So one-to-one functions. Every input in the domain gives an unique output in the range. One-to-one functions must pass the vertical horizontal line test. One other thing, I already stated it, but let's just put it on there. To solve for inverse functions or to find an inverse function if it exists, you're going to swap x and y and solve for y. And once you get y by itself, and there's no other y in that equation, that is your inverse function. So to find, f inverse of x, if it exists. So first thing I do is I rewrite my function notation, f of x or g of x, h of x, whatever it is, as y. If it's not already done so. And then once you rewrite that as y equals something, now you're going to go and interchange your x and y values. So wherever you see an x, you're going to plug in y, and wherever you see a y, you're going to plug in x. So swap x and y's. So once you've done that, you're going to solve for y. Once you solve for y, rewrite y as f inverse of x. And it doesn't hurt to check. And you would check by showing that the composition, either way, you took it, you would have gotten back x. Okay, so I kind of just gave you a review all of inverse functions, one-to-one functions from 6.2. And so let's just do some quick examples. So in this case is f of x one-to-one. Well, in order for it to be one-to-one, it has to pass the horizontal line test. Here's one example where I draw a horizontal line and it's intersecting in more than one spot. And so, no, this is not one-to-one. It fails the horizontal line test. So sometimes when functions are not one-to-one, it's helpful, and we can do this, we can limit the domain and make it a one-to-one function. So basically, if I said, okay, well, if we said x has to be, if you had f of x is equal to x squared, and we set a restriction here and we say x has to be greater than or equal to 0, if you look at the graph of that, that's just the right-hand part of the parabola shape. And now if we ask, is this one-to-one? If we draw a horizontal line anywhere on here, anywhere we draw a horizontal line, it's only going to intersect this once. And so it is a one-to-one function. And so if you've done trig before, you've noticed that in order for trigonometric functions to be one-to-one, you had to limit the domain in order to have an inverse function. Let's say you're given a graph And we have some points. Let me just draw this. So it looks like we have a point at -2, -2. We have a point at -1, 0. We have a point at 0, 1. And we have a point at 1, 2. My graph doesn't look good at all. I don't like that because it's just not. It's not forming the same shape. That's why. Because 1, 2, I was at 1, 3. That's why. Okay. And the graph of a one-to-one function f is given. Draw the graph of the function f inverse of x. So this is f of x. You'll notice it's 1-to-1. If we draw a horizontal line anywhere where this is defined, it's only defined between -2 and +2, or -2 and +1. But for f of x, now we want to graph f inverse of x. Well, any point in the form xy on f of x are swapped. The x and y coordinates are swapped, is yx on f inverse of x. So this point here at -2, -2, and then we had a point at -1, 0. We had a point at 0, 1. And we have a point at 1, 2. And so -2, -2, swapping x and y doesn't do anything. It's still at -2, -2. So we have this point here. -1, 0 now becomes 0, -1. 0, 1 becomes 1, 0. And 1, 2 becomes 2, 1. If you look at the dotted line, y equals x, this should be a mirror image across this line. Which it pretty much is. Okay, so we could tell that we did that right. Okay, so find the inverse of f inverse and check your answer. That's part A of what we're going to do. B, find the domain and range of f and f inverse. And C, graph f and f inverse and y equals x on the same coordinate. I'm going to just get a new page because I don't like how skinny my pen is getting. Okay, so we're given that f of x, it's really thick, is equal to 4 over x plus 2. And we want to first find f of x, I'm sorry, and f inverse of x. Okay, so first step, we're going to swap our x and or we're going to rewrite f of x as y. So this is y is equal to 4 over x plus 2. Swap x and y. So instead of y equals, we have x is equal to 4 all over, see an x there, I'm going to replace it with y plus 2. And so now we want to solve for y.
Yeah.
We have an
यार
inequality.
निशी लेकिन हाँ किया everything बहुत सी like इन्नी समझ होंदी सी.
Okay, so solve for y.
उदा कहंदा
Solve for y. So you need to get rid of the denominator. So let's multiply both sides by our denominator. That way we can clear our fraction. So if we multiply both sides by y plus 2. The whole point of that was so that fraction goes away. And so those cancel. This y plus 2 and this y plus 2. And we're left with, let's distribute our x. So we're left with y times x plus 2 times x is equal to 4. So there's multiple terms with multiple variables, but we want the term with a y because we want the y by itself. So we want all the terms with y by itself on one side of the equal sign and all the terms without y on the other side. And so if we subtract 2x on both sides, well, those aren't like terms on the other side. So we have yx equals 4 minus 2x. And in order to get y by itself, we now need to divide both sides by x. So y is equal to 4 minus 2x all over x. And then we're going to rewrite y as f inverse of x. So f inverse of x is equal to 4 minus 2x all over x. So I wanted us to show that what we did was right. So I'm just going to write f of x down here to help me so I can scroll up. F of x is 4 over x plus 2. So let's show those are inverses of each other. So we want to show it one way. It doesn't matter. You can show it either way. So we need to show that one way, we take the composition, doesn't matter which one, we're going to get back x. So if I go in and I plug in f inverse of x. Which one is that? That's this equation. Wherever I saw an x. So 4 minus 2x all over x, wherever I see an x and f of x. So let's rewrite f of x and put parentheses wherever we see an x. So this is f4 all over. You see an x there, put parentheses, big enough to rewrite that. And then outside is a plus 2. So complex fraction, you can clear this by multiplying by the LCD of the fraction within the fraction. Well, there's only one fraction within the fraction, so that LCD is x. If we distribute, well, there's only one term in the numerator, so, and nothing cancels, we have 4x all over, but the x times the first grouping, 4 minus 2x over x in the denominator, x's cancel. We're left with 4 minus 2x. Distribute the x to that other term, plus 2. So that gives us 2x. Simplify, combine like terms in the denominator, negative 2x plus 2x cancels, so we're left with 4x over 4, which is equal to x. So we showed what we wanted to show, and what we did, we found the correct inverse. And then part B. Where did I say? Find the domain and range of f and f inverse. So find the domain and range of f and f inverse. Okay, so let's look at f of x. F of x, that was the 4 over x plus 2. Only problem spot we're going to have there is when x sets the denominator equals 0. So the domain here is going to be all reals, except x can't be negative 2. So that's our domain. So f inverse of x, this is equal to, which was that? That was the 4 minus 2x over x. Okay. So this is undefined. Our domain is going to be all values of x such that, but in this case, x can't be 0. Our domain and our ranges are swapped. And so if I know the domains of one, then I know the ranges of the other. So the domain here, x could not be negative 2. So that means for my range, of f inverse of x equals the domain of f of x. Except the only thing is that's different is it's y instead of x. So our range is y has to be such that y cannot equal negative 2. So because of this, my range of f of x is the same as my domain of f inverse. And so my range is going to be y such that, well, y can't be 0. And we'll see more of that, and we can verify that when after we graph it. Okay, so there's multiple ways we can do this. Let's look at 4 over x plus 2. We can look at this as 4 over x, or our parent function 1 over x, and we can treat this with transformations, that x plus 2 in the denominator. That's transposing my 1 over x, my parent function, to the, it's plus 2, so left 2 units, and this 4 is stretching it, making it grow faster. Or I can use my fact that we were just graphing rational functions. I know I have a vertical asymptote, which sets my denominator equals 0, but not also my numerator. So I know that x equals -2 is a vertical asymptote. I know that I have a horizontal asymptote here. My horizontal asymptote, my degree of my denominator is larger, so I have a horizontal asymptote at my y-axis. And like we said, it's just stretching it now. And so my piece is going to look like this over here and this over here. And I can get some more points if I wanted to. So let's say I plugged in -1 here. I would get 4 over +1, which is 4. If I plug in 0 for x, I get 4 over 2. So that's 0, 2. Like I said, I already knew what that shape was going to look like because of transformations and asymptotes. So this is our f of x function. And then over here, on the other side of -2, if we plugged in -3, that's 4 over -3 plus 1. That's 4 over -1, which is -4. So at -3, we got -4. And come down and hug this. Maybe choose another point. If we plug in -4, we get 4 over -4 plus 2 is -2, so 4 over -2 is -2. So at -4, we get -2. So this is f of x. So we can graph the other function by using things that we know about the function. F inverse of x, f inverse of x. Where was it? It's way up here somewhere. I thought I wrote them down. Here it is. We can graph this by swapping our x and our y value, or we can rewrite this a little bit. If I broke this up as 2 separate fractions, my f inverse of x could be rewritten as 4 over x minus 2x over x, but minus 2x over x, those x's can cancel, leaving me with a -2. So technically, this, if I use transformations to talk about it, that -2 outside of the 4 over x, that's shifting it vertically down 2 units. And the 4 over x, that 4 is just stretching it. Okay. So another thing to think about it is our inverse function. What do we know? Our vertical asymptote here is at 0. That's the value which sets our domain, or is undefined, our denominator equal to 0 and not our numerator. What else can I say about this? And I have a horizontal asymptote. The degree of the numerator and denominator are the same. So that's the leading coefficient of the top over the bottom. So -2 over 1, which is -2. Before I get any further on that graph of f inverse of x, let's just go back really quick and talk about the domain and range of f of x. So if you looked at that black graph, notice that the only value that we can't hit is -2, which is our domain. And notice that we're hitting all of our y values except for when x is 0. That's where our horizontal asymptote is. And that's what we said here for our range by noticing what the domain of our inverse function was. So I just wanted to, I said that we were going to go back and verify those were correct. Okay, so we talked about shift, we talked about asymptotes for f inverse of x, and so now we can graph it. And so because this is now here, I know this is down here. Okay, so this point 2, because I also know refractions, this was 0, 2, I know 2, 0, so point. Just to help me with a couple more points. -1, 4 was a point, so I know 4, -1 has to be the point on the inverse function. So our graph looks like this. For f inverse of x. And then we know that this piece here, this is below, but it's shifted. It's shifted this way. And so let's just name a couple of points that we had over here. We had seen a point that was at -3, -4. That's now becoming -4, -3. So -4, -3. Oops, that's wrong. -4, -3. And this point here was -4, -2. And so that's -2, -4. And so it looks like this. The other thing they wanted us to graph was that line y equals x. And if you folded the paper, they should be a mirror image across that line, which it's hard to tell. If you look though at our red graph, notice our domain is everything except for x equals 0. And our range, we're hitting all y values except for -2, which was the swap of what we had before. So kind of putting everything together. And it was kind of cool because it put together a lot of different sections that we had talked about in this course. I don't know if you can see that. Okay, let's look at one more. From this section. So here we're given f of x is equal to 2 square root x plus 3 minus 5. The function f is 1 to 1. Find its inverse and check your answer. Find the domain and range of f and f inverse. Okay. So we want to find f inverse of x, and we want to find the domain and range. Let's talk about the domain here, because the domain of this is going to be the range of our inverse function. We have some problem spots. We can't have any negative numbers underneath an even powered radical. And so we need our values for x plus 3, what's underneath the radical, has to be greater than or equal to 0. And so this is a linear inequality. We solve these differently than nonlinear inequalities or rational inequalities. So solve it just like it was in equal sign. Get x by itself. So we get x is greater than or equal to -3. We didn't divide or multiply by a negative, so our inequality is the right direction. So we know that this is going to be the range of f inverse of x is y is greater than or equal to -3. Okay, so to find f inverse of x, we're going to rewrite our function as y equals 2 square root of x plus 3, and then outside of the radical -5. We're going to swap our x and y values. So we have x is equal to 2 square root of y plus 3, and then -5. We want to solve for y. So just like we were solving equations with radicals, you wanted to isolate one of the radicals that only has one. So isolate that radical, let's add 5 to both sides. And adding 5 to both sides, we would get x plus 5 is equal to 2 square root of y plus 3. And we need to get that 2 on the other side, so we can get that 2 to the other side by dividing both sides by 2. So we have x plus 5 all over 2 is equal to the square root of y plus 3. Get rid of the radical, square both sides of our equation. So we get x plus 5 quantity squared in the numerator all over the denominator squared, which is 4, equals y plus 3. Let's get y by itself, subtract 3 on both sides. So we get our inverse function, f inverse of x. Be careful, because that really isn't in the denominator. It looks like it is there, though. Is equal to x plus 5 quantity squared all over 4, and then a -3 outside. So we know what the range is. What about the domain? So we know the range of f inverse of x, y is greater than or equal to -3. The domain, is there any trouble spots in here? Is there any variable in the denominator? And so the domain of f inverse of x is all real numbers. There's no trouble spots. There's no variables in the denominator, and there's no radicals. So domain is all reals. Which means my range of f of x is equal to what my domain was here, which was all reals. So my range of f of x is all reals. one more thing we want to show is we want to show the composition. So one way taking the composition would give us back x. So let's go in wherever we see an x, in f of x, we're going to replace it with x plus 5 quantity squared all over 4, and then the minus 3. Okay, so f of x, this was equal to 2 square root x, so put a parentheses, and underneath the radical was a plus 3, and then outside the radical was a minus 5. Okay, so let's plug that in wherever you see an x here. So we have x plus 5 quantity squared all over 4, and then a minus 3. Okay, so simplify and let's show that this is the same thing as x. So we have 2 square root. Well, we technically don't need those parentheses around here. It just kind of helps us to show where we're plugging x in. And so notice our negative 3 and plus 3 cancels. So we're left with x plus 5 quantity squared in the numerator all over 4. And then outside of the radical, we have this minus 5. So this is 2. Well, the square root of a fraction is the square root of the numerator. So square root of x plus 5 quantity squared is just x plus 5. All over the square root of the denominator, square root of 4 is just 2. And then we have a minus 5 out here. 2's cancel. So we're left with x plus 5, and then this minus 5, which is equal to x. So we showed that it is. Okay, so that right there is 6.2. So hopefully that was just review and that came back really easily for you if you forgot that. Any questions? You want some problem? Okay. So let me give you a couple questions to try. And then we'll take a break. So let's first try. What if f of x is equal to x squared minus 4 all over 2x squared? They actually give you a stipulation, and that's probably to make it that it's 1-to-1, that x has to be greater than 0. So for that, you want to find f inverse of x. And check your answer. In part B, find the domain and range of f and f inverse of x. Okay, so why don't you guys take a moment and try that. Okay, so we're looking at an example that's similar to the one that you guys were trying. And we're going to do the same thing. We're going to find the inverse of the function, and then we're going to find the domain and the range of f of x and f inverse of x. Also, we're going to show that what we had found for the inverse function was truly the inverse function by taking the composition of the two functions and showing that we get back x. So to find the inverse of this function, we want to rewrite our function as y equals x squared plus 3 all over 3x squared. So instead of function notation, it's y. Now go back in and rechange wherever you see x, rewrite it with y, and wherever you see y, rewrite it with x. So we have x then is equal to y squared plus 3 all over 3y squared. So we want to solve for y here. And so because we have an equation, we can clear that equation by multiplying both sides by our denominator. So let's multiply both sides by 3y squared. So doing that, we have over here, we have 3xy squared is equal to 3y squareds cancel here, y squared plus 3. So we're trying to solve for y. I notice there's multiple terms with y in here, and so what we need to do is we need to get all the terms with y on one side. And so let's subtract y squared on both sides. So we get 3xy squared minus y squared equals 3. Because we want y by itself, and there's two terms with y in there, and they're not like terms because one has an x and one doesn't. Let's factor out the y, because that's what we want to get by itself, out of that equation. And so if we pull y squared, actually factor out y squared, we're left with 3x minus 1. It still equals to 3. So now we can get y all by itself by dividing both sides by that 3x minus 1. And so we get y squared then is equal to 3 over 3x minus 1. And we can get rid of the square by taking the square root of both sides. And so we get y is equal to plus or minus, I'm going to put a question mark here. We got to go back and check this in a second. The square root of 3 all over 3x minus 1. Okay. So the reason I'm saying we need to check that plus and minus is because our problem, we started out with a stipulation. If we would have graphed this without this stipulation, this would not have been a one-to-one function. And so they narrowed down the domain, so it made it one-to-one. And so our domain of f of x here, notice, is greater than 0.
Are we allowed to reduce that or no?
Excuse me?
Are we allowed to reduce the fraction or no? Because it reduces to x minus 3.
It doesn't reduce because 3x minus 1, there's two terms in the denominator.
Oh, okay.
Yeah. So the domain of f of x, x is greater than 0. So this is actually our range. So this is going to help us. This is our range of our inverse function. So that means we are going to be getting back positive numbers for our range. And so if we're going to get back positive numbers for our range, that means that we couldn't have that negative in front of the square root. And so for f inverse of x, this is equal to the positive of the square root of 3 all over 3x minus 1. And so since we've done that, we might as well go ahead and talk about the domain of f inverse of x, which will be the range of f of x. So the domain of f inverse of x? Well, we have a couple things that can cause us problems. We have a radical, so we can't have any negatives underneath an even powered radical. And we have a variable in the denominator, and we can't have 0 in the denominator. So we know that 3 all over 3x minus 1 has to be greater than 0. And 3x minus 1. Actually, this can be greater than or equal to 0, but 3x minus 1 cannot equal 0. So let's solve for 3x minus 1 is equal to 0. If we add 1 to both sides and divide by 3, we get x by itself. So x can't be 1/3. And then this is a rational inequality. So we solve those a little differently. That's where we had to find out where it was undefined and where the denominator was 0. And so that was only undefined at 1/3, which it can't be. And so if we test, if we plug in a number to the left of 1/3 to see if it's true or false, if we plug in 0. If we plug in 0, we get 3 over 3x minus 1, or 3 over 0 minus 1, which is 3 over -1, which is negative. And so this is false. This was not going to be part of the solution. If we choose a number to the right of 1/3, so 1, we plug it in here, we get 3 over 3 times 1 is 3 minus 1. So that's 2. 3 over 2 is greater than 0, so this is true. And so in order for this to be true, it has to be everything that is greater than 1/3. So the domain of this is 1/3 to infinity.
So why can't it be between 0 and 1/3?
If you choose a number in between here, you'll see that it's also false. 0 was the value I just chose to the left of 1/3. So you have to just choose one point when you find the critical numbers, which 1/3 is the only critical number here. It's the only number that sets the this rational inequality undefined. So notice if you plug in 0, it's undefined. But if I choose a number in between here, so 0.25, and I plugged it in here, I would also get a false statement. Anything I chose to the left of 1/3 would give me a false statement. And anything I chose to the right of 1/3, you plug it in for x, you'll get a true statement. So sometimes when I plot these, I plot, all the critical numbers. Like in this case, though, there was only 1. So that domain of my inverse function is my range of f inverse of x. So instead of x has to be greater than 1/3, it's y has to be greater than 1/3. Or I could write that in interval notation also, 1/3 to infinity. Okay. And so the last part was checking. So showing that our inverse, what we got for our inverse function was truly our inverse function. And so if we take the composition of our two functions, so let's look at f of x. So f of x again was equal to x squared plus 3 all over 3x squared. So we can either take f inverse of x and we can plug that in wherever we see an x and simplify, or we can take f of x and we can plug it in wherever we see an x and f inverse of x and simplify. And either way, we should get back x. And so if we look at f of the inverse function, let's just go in here. We're going to be plugging in the inverse function wherever we see an x and f of x. So put parentheses, enough to plug in that whole expression, plus 3 all over 3 parentheses squared. So wherever we see an x or parentheses where we put the x, we're going to put in the square root of 3 all over 3x minus 1. Well, if you square square root, that cancels each other out, and you're left with what's underneath the radical, which is called the radicand. And so we would be left with 3 over 3x minus 1, and then plus 3, all over 3 times, again, square and the square root cancel out, so 3 all over 3x minus 1. Again, we're dealing with a complex fraction, and so we're going to need to simplify. So let's multiply by the LCD of all the fractions within. Well, the only common denominator or only denominator of the fractions within is 3x minus 1. So we're going to multiply by a fancy one, 3x minus 1. Over 3x minus 1. If it helps you to put a 1 over the 3x, under the 3x minus 1s, then do that. So you can see it as fractions. So distributing the 3x minus 1 to the first grouping in the denominator, those 3x minus 1s cancel, and you're just left with a 3. Plus, and if we distribute it here, we're left with 3 parentheses 3x minus 1. All over. So distributing it here, there's only really one term down here. And so this 3x minus 1s cancel. And we're left with 3 times 3. And I could write that as 9. So let's distribute, let's simplify. So we have 3 plus, distributing our 3 in the numerator, we have 9x minus 3. All over 3 times 3, which is 9. 3's cancel in our numerator, so we're left with 9x over 9, which now we can simplify, which gives us x. Showing that what we truly did get for f inverse of x was correct. So a couple of things can happen. If you did not find f inverse of x correctly, then you're not going to get back x when you do this. And the other thing is, if you do find f inverse of x correctly, but you go back in and take the composition and you don't plug it in right or you don't simplify right, something's wrong with your arithmetic or algebra, then you might have problems getting back x. So if you don't get back x, you got to go back and figure out where your math is wrong. Okay, so hopefully that helps. And you would be able to go back. If you weren't able to do it, just try it. Which was here. So if you didn't write that down, write that down. I might ask you guys to turn that in later. And so just be able to access that. Okay, so I'm going to jump into exponential functions, and it's inverse. And the inverse function, which is the logarithmic function. So this is exponentials. This is on 6.3 and logarithms are in 6.4 and on. So exponential functions. So exponential functions are in the form of f of x equals b all raised to the x power. So b is some number, and b, in order for it to be an exponential, it has to be greater than 0. Other stipulation is that b can't be 1. And the reason that stipulation is there is if you had a base that was negative and x is the thing that is changing, that's the thing that is varying. And so if you start plugging in numbers, you're going to have even and odd numbers. That's going to bounce that point back and forth, and it doesn't form an exponential equation. If b was 1, 1 raised to any power always gives us back 1. And if you graphed that, that's a horizontal line, which again is not an exponential function. So those are stipulations that need to hold in order for it to be exponential. Graphing your exponential function, it depends on your value of b. If b is bigger than 1, then it's going to have the following shape. So this is the graph of f of x equals b to the x if b is greater than 1. Makes sense that, notice our y-intercept. Our y-intercept is at 0, 1. So this is when x is 0. Remember, if you raise a number other than 0 to the 0 power, you get back 1. And so notice that our y-intercept is always going to be at 0, 1 when it's in this form. And notice that there's no value that you can plug in for x to get this y value to be 0. Any number you choose, positive or negative, your y value is always going to be positive and it's never going to hit 0. And so this graph, we have a horizontal asymptote at the line y equals 0. We have a point at 0, 1. This graph is strictly increasing. So we talked about when graphs are increasing and decreasing, looking at this graph, if you're moving left to right, it's going upwards. That's the informal definition. So graph is strictly increasing. Okay, if our value was between 0 and 1, that changes the shape of our graph. And so if b is between 0 and 1, couldn't be 0 or 1 because they're not defined as a function, then our graph ends up being a reflection of this across the y-axis. So it looks like this. And so same sort of idea. You have a horizontal asymptote. There's no value here that could give you your y value of 0. And you have a point here at 0, 1. So horizontal asymptote at y equals, it's the equation of a line, 0 and point at 0, 1. This time though, the graph is strictly decreasing. So why is that this, I said, was a reflection? Notice that reflections across, and we talked about this, the y-axis. So a reflection across the y-axis is changing your x value. Let's go in here and let's change the x value. And so let's go back here and let's define f of x again to equal b to the x, b greater than 1. Now if we looked at f of negative x, this is equal to b. So we would go back in and now we're playing in negative x wherever we saw an x in f of x to the negative x power. Rules of exponents are really important to remember and very, very helpful in math. And so I'll go back and I'll review those in a second. I should have done that. But there's a rule that says power to power of exponents is multiplication. So we can rewrite this a little bit if we want. Let's rewrite this as b to the negative 1 power over x, or times x. Well, remember, if you have a negative exponent, we can rewrite it and make it positive. So this would be 1 over b to the x. We said that x was greater than 1, so 1 over a number greater than 1 is a number between 0 and 1. And we talked about, again, changing our value of our x sign is reflection. Across the x-axis. Okay, kind of a different way that you might have looked at it before. And so a lot of times when I start teaching this and again, just reviewing this, I would have shown and I would have chosen a value b greater than 1, and we would have plotted points, plugged in value for x, and then found our y values, plotted it. And I would have told you that that was the general shape. I wanted to go back. Why did I want to go back and tell you? It was really important, but not important to remember. Okay, maybe, oh, I know. So I wanted to go back and I wanted to review rules of exponents. And we're going to use these, and you'll use them again further on in your math careers of manipulating things. And so if you have same base and there's multiplication in between, you add your exponents. So b raised to the m power times b raised to the nth power is equal to b raised to the m plus n power. We just saw, and I referenced to power is a multiplication. And so this would be b to the m raised to the nth is b to the m times n. If you have a negative exponent, we can rewrite it and make it positive by putting it down in the denominator. If it was already in the denominator, we could make it positive by moving it up into the numerator. What else can I? B raised to the 0 power is 1, where b can't be 0. Division, if you have division, same base. Well, if m is bigger than n or equal to, I usually take it where I look at the exponent on top minus the exponent on bottom. But if n, the denominator was bigger than the degree on the top, then I would actually move it down to the denominator and do n minus m as the exponent. That just saves a step so that I don't have to deal with a negative exponent in the numerator because the denominator was bigger and it's negative, and moving it down. Okay, so those are rules of exponents that hopefully you remember. If not, make sure you do. Oops, actually one more, and we already referred to it today, was with rational exponent rewriting it as a radical. And so if you had b raised to the m divided by n power, this is equal to the nth root of b raised to the m. Or if you're trying to simplify and your value of m is bigger than n, it's easier if you first take the nth root of b, if possible, and then raise that result to the m power. That way you're not dealing with a radical of such a huge number, and it's easier to handle. Okay, So knowing the rules of exponents, that's going to help us. And graphing, knowing the general shape, depending on your base, if it's bigger than 1 or between 0 and 1, it's also going to help us. And that's what will help us graph. And so let's look at some examples. And now we can use transformation of functions, which we've learned in the past, to graph. So if it said f of x is equal to 3 to the negative x minus 2. And actually, before I graph this, because it wants us to determine the domain and range, horizontal asymptote, y-intercept of each function. Let's go back up here and discuss the domain and range. We kind of looked at what the shape was. I told you, it was increasing. We just found where the asymptote was. But notice that our domain and range for each one is, the domain is all real numbers. So there's nothing that we have to worry about plugging in for x. We can plug any real number in there and we'll get back a real number. The range though, notice that I said we wouldn't get any y value equal to 0. So there's not going to be any point on the x-axis. There's no y value that you can, or x value you can plug in to get a negative number. And so our range is going to be 0, but not including y is greater than 0. Or another way to write that is 0, parentheses 0, comma, infinity. Okay. So going back to our example, it wants us to graph this. Find intercepts. The domain and the range. Oops, domain, range, and asymptotes. Okay, so a couple of things I can do. I can look at what my parent function is and the transformations that I would do to that graph with these different things added to it. And my parent function would be y equals 3 raised to the x power. I think they called it something else besides parent function. But basically, we were doing transformations on this graph. And if I looked at this graph, y equals 3 to the x, again, I have a point at 0, 1. If I plugged in 1 here for x, I get y is 3. But I'm not really wanting too much plot points. If I plug in negative 1, 3 to the negative 1 power, negative exponent, bring it down is 1/3. Okay, so we get this graph. So let's talk about what this minus sign is doing right here and what this -2 is doing right there. And so this minus sign inside here, that's like if we had looked at f of negative x, or let's say this is g of x. If we plugged in negative x, that would have given us 3 to the negative x power. If I plug in negative x here, that's affecting my x value. So again, that's a reflection across the y-axis. And so this negative in front of the x tells me there's a reflection across y-axis. So if I did that, that would look like this. And so this piece right here is y equals 3 to the negative x. Or maybe I should just write it as g of negative x. And then the minus 2 outside of that, that's affecting it vertically. Vertically was always the last thing that we did when we did the transformations of the graph. And so the minus 2, this shifts the graph down 2. And so I'm taking this purple graph now, which is basically g of negative x, and then minus 2, which is equal to my f of x graph. So if I shift that down to my point that was at 0, 1, is now going to be at 0, negative 1. My horizontal asymptote, which was on the x-axis, is now going to be at y equals negative 2. And so it's just the graph above shifted down 2 units. Okay, so we got our graph. Which we have the general shape. What if we wanted to figure out what the y, I'm sorry, not the y-intercept, got that, what the x-intercept was? Well, we don't have that tool yet. Notice if we wanted to do that, we would be setting y equal to 0. So if we have 0, x is equal to 3 to the negative x minus 2. X-intercept occurs when y is 0. If I added 2 to both sides, I'm looking at when is 2 equal to 3 to the negative x. Our variable is in the exponent. And so in order to get that variable out of the exponent, we need to introduce logarithms, which hopefully we'll have a time. I don't think we'll have time to do that today. Okay, so I don't know what my y-intercept is, but I do know what my general shape of my graph is. And I can answer what the range is. My range is now changed. My range is y has to be bigger than or equal to negative 2 now. We shifted our y equals 0 down 2 units. Our horizontal asymptote, which was y equals 0, is now y equals negative 2. And our point that was 0, 1 has transformed to 0, negative 1. That's what they wanted. Or our y-intercept. They just want a y-intercept.
So are we just supposed to memorize the shape of the graph of the parent function?
Yeah, you should know the general shape of the graph depending on what the base is. And then now, instead of having, like before in intermediate algebra, we had to just go in there, we plotted points. If it wasn't in a general form, but now we can use transformation of functions that we know learned to do, transform these graphs to graph them. I mean, you could still plot points, it's just gonna take longer. And in future classes, you just need to be able to recognize that pretty fast and be able to graph it. Okay. Let me pull another one. The exponents are really small. I used to not have a problem with those. So what if it was f of x is equal to 2 plus 4 raised to the x minus 1 power. So here, I notice this is exponential because it's 4 raised to a power. So I know that my parent function, or the general shape that I need to know, is, let's just call it g of x or y, equals 4 raised to the x power. And so we're trying to figure out what is that minus 1 doing to our graph, and what is this plus 2 doing to our graph. And so the plus outside of the exponential is always vertical. And so this is going to be the vertical shift, but we don't do that until the last part. So this is shifts up 2 units. Horizontal shifts are the first thing that you apply when we're doing transformations of a graph. And horizontal transformations occur with what you're adding or subtracting to your x value, as if you had plugged it in wherever you saw an x in this function. So that is going to shift my graph. And this minus 1 is telling me I'm shifting it actually to the right one. So shift g of x to the right one. Okay. So we can put that kind of together. I know that y equals 4 of x. 4 is bigger than 1. My base is bigger than 1. And so it's going to be this general shape. And so let's just talk about important points. So this point here at 0, 1. Well, if I shift that point 0, 1 to the right one, my x value now is 1. And now I'm going to take that point 0, 1 and I'm going to shift it up 2. And so if I shift that point up 2, that's now going to give me a y value of 3. So now it becomes 1, 3. My horizontal asymptote for g of x was y equals 0. But I shifted everything up 2 units here. And so my horizontal asymptote for my f of x is y equals 2. So maybe put a dotted line there. And so basically, we know the general shape, what it was before, and this just shifted a little bit over to the right and up 2. And so same kind of shape, you have something that looks like this. So notice all of these graphs of our exponential functions. If we did a horizontal line test, they pass them. So if we did a horizontal line anywhere where this is defined, where it's defined everywhere, it's only going to intersect that graph once. Even though this looks like it's getting really, it would be like a horizontal line, it's not. It's actually decreasing and never going to hit that line, but it's always something different. Let me just go over one more because I didn't look at the negative in front. How about f of x is equal to 1 minus e raised to the x. If it helps you to rewrite it, that constant really, if you want to know, is negative. This is negative e to the x plus 1. I don't know if that helps you recognize the vertical shift more, but they're the exact same thing. So that plus 1, again, is a vertical shift. But it's up 1. This negative, though, this negative here, that's affecting our y value. So really our parent function that we would be graphing, g of x, that g of x function is just e to the x. Just recall e is just a number, just like pi is a number, and it represents the number. It goes on infinitely. It's irrational, but it's approximately 2.718, I believe. I might be off a little. That's not going to affect anything. So notice that e is greater than 1. So we know what the general shape of our graph is. This negative, in order to get the negative out here, we would have had to multiply our y value by -1. And so this changes the y value. And so it's a reflection. Changing y reflects it across the x-axis. Okay, so if we looked at this, so our general graph of y equals e to the x looks like this. That minus in front reflected across the x-axis. So it's going to look like this. So this is an important point here, our y-intercept, which is at 0, -1 now. And now we just need to shift this purple graph up 1 unit. And so notice that this negative e to the x, our horizontal asymptote didn't change. It's still y equals 0. But if we shift everything up 1 unit, our horizontal asymptote now is at y equals 1. And our point here, shifting it up 1 from 0, -1, now is at our origin, 0, 0. And so we got the general shape of what our graph looks like. We have our y-intercept. Actually, our x-intercept too is at 0, 0. We have our horizontal asymptote is at the line y equals 1. We have our range. The range has changed. We're hitting all y values from -infinity all the way up, but not including +1. It's another thing that you need to know or remember is when you're solving exponential equations, if you can get it in the form that you have some exponential equation equal another exponential equation, and they're the same base, then we can just say then that m is equal to n. As long as we have to put a couple stipulations, b can't be 0 and b can't be 1. Let's just say b has to be greater than 0. Okay, so sometimes when we're trying to solve exponential equations, so we're trying to solve for the variable and the exponent, we can manipulate these bases to be the same. And so for this section, all of these bases you can manipulate to be the same. A lot of times we can't manipulate the bases to be the same, and then we're going to use logarithms, which we'll introduce tomorrow, to do that. Okay, I have a couple minutes and then we're pretty much done. So let me just throw out a hard one real quick. Maybe, okay, let me kind of hard. So how about 4 raised to the x times 2 raised to the x squared is equal to 16 squared. So it's just saying, the equation is saying solve the following equations. And so again, our goal, I noticed that 4, 2, and 16, which are all bases, can be manipulated to be base 4 or base 2. Just make sure I wrote that down right. I did. So we're going to manipulate all these to be base 2, and then we're going to use rules of exponents. Okay, so 4 I know is the same thing as 2 squared, right? And so we have 2 squared is 4, and that's all raised to the x power, times, well, this is already base 2, right? And that is all raised to the x squared. Is equal to, and 16 can be rewritten as base 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's 2 to the 4th power, but that 16 is all squared. Okay, so rules of exponents. We talked about power to power is multiplying. And so this 2 squared raised to the x power is the same thing as 2 raised to the 2x times 2 raised to the x squared is equal to, again, power to power is multiplying. So 2 to the 4th is raised to the 8th. Again, rules of exponents. We can multiply our exponents, same base, we have 2. So we have 2x times x squared. That gives me 2x cubed is equal to 2 raised to the 8th power. Okay, so we did what we wanted. We manipulated both sides of our equation. We got the same base for each exponential. It is only a single exponential equals single exponential. If I had some plus constant or variable out there, some more terms, I couldn't do this. But because this is true, we can now say that 2x cubed, same basis, then has to equal 8. And so we can use our rules of solving this type of an equation, divide both sides by 2, isolate x cubed. We get 8 divided by 2 is what, 4? Take the cubed root of both sides, we get x is equal to the cubed root of 4. For some reason, something looks like it's off. It's telling me my solution is -4 and 2, which is nothing like I just got. So I will look into that. I know I already kept you over a couple minutes, but I'll look into that and I'll look at where my error is. And I think I'm just going to pause this video, let you guys go, and then record the rest once I figure out what I did wrong. Okay, let me pause this. And you're welcome to